going to talk about the unique factorization of tensor products, which is joint work with Venkatesh, who's still not here, I guess. Okay, so the setup that we're going to start with is G, finite dimensional simple Lie algebra over the complex numbers. So for example, you can think of G as SLN C, the trace zero matrices, or say the symplectic Lie algebra, or the orthogonal Lie algebra, or well, one of 5 Lie algebras. Now, the theorem due to Rajan, I think the early 2000s, states the following, that if you have a representation of G which can be written as a tensor product of finitely many irreducible representations, then it has a unique such expression up to reordering of the factors. So let me just write this out. If V1 through Vn, W1 through Wm are non-trivial, finite dimensional irreducible representations of G such that tensor product of the Vi is isomorphic to the tensor product of the Ws, then n equals m, and there exists a permutation sigma of 1 through n such that Vi is the same as W sigma I. Okay, so it just says up to reordering of the factors, these two expressions are really the same. And a minor reformulation of this, which says, well, here notice that allowing non-triviality, I mean imposing non-triviality of the representations is important, because if you allow trivial representations, then of course you could tag along any number of trivial factors, and of course there's no way you could make n equals m. So the theorem would be false unless you said you only allow non-trivial representations. Alternately, you can allow trivial representations, but the choice that n equals m. So alternately, you can there's an alternate version sort of implicit in the way Rajan proves it, for example, which is you fix n equals m to start with, but then you allow trivial factors. Okay, so let me again write this out. So let's say we have VIWJ, finite dimensional irreducible representations of G for ij between 1 and n, such that tensor product of Vi is the same as the tensor product of the Wj's. Then there exists a permutation sigma such that Vi is the same as W sigma I for all. And notice that these two are just equivalent formulations, because theorem implies theorem dash, right, clearly. Now, sort of for the converse, if you had the statement of theorem dash, theorem, what you would do is to just equalize the number of factors on both sides by tagging along a bunch of of trivial representations if you need to. Then you would be in the equation of theorem dash, tell you that both sides are the same up to permutation, and that would automatically tell you that n must have equaled m to start with, because if not, these extra trivial factors you tagged along must have been isomorphic to some pieces here, right? And that is, you assumed everything here is non-trivial. So this basically says you might as well think of theorem dash as being the statement one sets out to prove. Now sort of another remark here is it's important to start with a simple Lie algebra. Remark G, suppose we ask what if G were just a semi-simple Lie algebra rather than a simple Lie algebra, then the statement is not true. I mean, if you think semi-simple but not simple, then the statement is no longer true. So you very much need the hypothesis that G is simple. So G semi-simple, not simple, implies this theorem is false. Okay, and that's because a semi-simple algebra is say a direct sum of several simple pieces, and the irreducible representations of a semi-simple Lie algebra would correspondingly be given by sort of taking an external tensor product of irreducibles of the pieces. So a semi-simple Lie algebra, which is not simple, would have the property that it's a tensor product of two irreducibles could remain irreducible. So that would already violate the statement we are looking for. So simplicity of the Lie algebra is important. That's something to keep in mind. Okay, so what I want to do today is to give a proof of this statement of theorem dash, which is sort of very different from Rajan's original proof, and because of the way it's formulated, it just generalizes without having to do too much to the case of infinite dimensional Lie algebras which share the same kind of structure as the finite dimensional ones, the so-called Kac-Moody Lie algebras. But I'm mostly going to focus on the finite dimensional case. So we recall a few facts. That we need to analyze these kinds of representations. So the structure of G modules, if G is a simple or more generally semi-simple Lie algebra. So firstly, the structure of G itself, the Lie algebra G has what's called the root space decomposition. Where H is called the Cartan subalgebra, and these G alphas are the root spaces. So G alpha itself, for example, is the set of all vectors whose commutator with elements of the Cartan subalgebra gives you the eigenvalue alpha. It's the eigenspace for the eigenvalue alpha, and these deltas are, well, the set delta is called the set of roots. It's a subspace. It's a subset. It's a finite subset of H star, the dual of the Cartan subalgebra. And let's see, what else do we want to say? Delta can be written as a disjoint union of two sets called the positive and negative roots. And amongst the positive roots, there is a distinguished set called the set of simple roots. So there is a set alpha 1 through alpha L belonging to delta plus, which is called the set of simple roots, or a base for the root system. These elements have several nice properties. So one of them being that they form a basis for H star. But in addition, the other property is that every element of delta plus can be written as a positive or non-negative integer linear combination of elements of the alpha i's. Similarly, for delta minus, things in delta minus can be written as a non-positive integer linear combination of the alpha i's. Okay, so those are the simple roots. Now the structure of modules, if V is a G module, then again gammas are certain eigenspaces. So it's called the weight space decomposition. Is the eigenspace consisting of all vectors on which the Cartan subalgebra acts via the eigenvalue gamma. Okay, so that's the weight space V gamma. So there is such a decomposition. Third, what irreducible G modules? So irreducible G modules are parametrized. I mean, they're completely known. We know what all of them are. They are parametrized by what dominant integral weights. So an irreducible G module is, so it's usually written V of lambda, where lambda belongs to, it's called the set P plus. This is the traditional notation, which is the set of dominant integral weights. So the finite dimensional irreducible representations are parameterized by dominant integral weights. And in what sense? Given a dominant integral weight, one constructs what's called a highest weight representation with highest weight lambda. So this lambda fulfills performs an important role in this module. It is what's called the highest weight. So among the weights, it's the highest with respect to some natural partial order. So lambda is, it's called the highest weight. Of the module V lambda, where what do I mean by that? It just means that if I take elements of, so if gamma belongs to the set of weights, so let me give that a name. So I said direct gamma in P of V, the set of weights of V. So P of V is a set of all gamma which actually appear in this decomposition. So what do I mean by saying that this lambda is in fact the highest weight of V lambda? It just means to say that any weight of V lambda can be written in form lambda minus something. So lambda is sort of the highest fellow, minus of minus ni alpha I, where the ni's are all non-negative integers. Okay, and one sort of pictorially thinks of this as, so there's lambda, and all other weights sort of lie, below lambda. So if you think of these as being the direction of minus alpha 1 and minus alpha 2, every other weight can be reached from lambda by sort of going along a certain number of minus alpha 1s and a certain number of minus alpha 2s. So they all lie below lambda in this sense. And further, in fact, not only are all the weights of this form, so clearly from here lambda itself, so there's a further fact that lambda itself is a weight, and further lambda itself is a weight of the module V lambda, and the dimension of the lambda weight space is 1. So I should have written this as, so if you take the module V lambda and you figure out what's the dimension of the lambda weight space, then that turns out to be just a one-dimensional space. Okay, so this is the structure of the module V lambda, which says that there is just a one-dimensional space of highest weight vectors, and there's lots more to the story. Every other vector in this module can be obtained from the highest weight vector by by action of Lie algebra elements and so on. So it's a cyclic module generated by the cyclic vector. Okay, so but these are the facts that I'm going to use. So one keeps track of a module by by using its weight space decomposition. We can try and keep track of just some part of the information. It's the so I put it in this sense. Given a module V gamma is the gammath weight space. So by V lambda lambda I meant the lambdath weight space of V lambda. Okay, so now what I want to do is to keep track of just the dimensions of the weight spaces. So if V is a G module, then let's define, it's called the character of V or the formal character of V to only be the generating function which keeps track of the dimensions of the various weight spaces. So at the moment I've thrown out information about how precisely the Lie algebra elements act on vectors and so on. I'm only remembering what the dimensions of my various weight spaces are. So this is called the formal character of the representation V, and so of course you should ask what are the E gammas here, what do those represent. So you can think of them just as being placeholders, right? For each gamma I just need some variable which tells me that the gammath weight space had this dimension. So you can think of these as just indeterminates, but sort of maybe the precise way to say it is you should think of it as an element of the group algebra of H star. So you think of this set of weights as being a subspace of the dual of H, in which case this expression here is it's a finite sum, and the E gammas are formal exponentials which form a basis for the group algebra over H star. Right? So you should think of it really as living in that space, but if you sort of put together some further information that we mentioned here about the structure of modules V lambda, so I'm going to now specialize to the character of the highest weight module V lambda itself, then you can actually do a little better than just saying that this is some element of C of H star, because there is this distinguished highest weight lambda here. So let's do the following. Let's imagine now what would this sum look like. So certainly lambda itself is going to be a weight of the representation V lambda. So you're going to get the formal exponential E lambda occurring with coefficient 1, because the dimension of that weight space is a 1, and you're going to get a bunch of other plus a sum of some coefficients E to the mu's, where we know what maybe we should call it gamma. We know what all the other gammas look like. All these gammas are less than lambda, where by less than I just mean they look like this, okay, and they are not equal to lambda. So that's going to be the form of the character of V lambda, and what we'll do is further pull out the E lambda and think of it as really a sum of the following form. So if you pull the E to the lambda out, what you are looking at inside is in fact a finite sum again. The terms which appear there look like E to the gamma minus lambda, and we know what gamma minus lambda is, right? It's in fact an integer linear combination of the simple roots, right? In fact a non-positive integer linear combination of the alpha i's. So if you sort of look at where this element belongs, this guy is actually surely in C of H star, but in something better. This is in the polynomial algebra by E minus alpha 1, E minus alpha 2, E minus alpha L. Okay, so you can think of it as sort of the monoid algebra of the negative root lattice and so on. But in any case, so you see, all I'm saying here, maybe in a fancy way, is that pretty much everything which occurs in this expression, things here are going to look like e to the minus alpha 1 raised to some positive power, e to the minus alpha 2 raised to some positive power, and so on, because gamma minus lambda itself, so all I'm doing is unraveling this term, it's going to look like e to the minus this summation ni alpha I, but I can rewrite that as e to the minus alpha I raised to the ni, so product of such terms, right? So it's a monomial in new variables, e to the minus alpha 1, e to the minus alpha 2, e to the minus alpha L, with non-negative powers. All the powers that appear here are non-negative. Okay, so that's what the character of a irreducible module looks like. Except for the leading factor e to the lambda, the rest of it really lives in this polynomial algebra. And sort of other facts about formal characters, well, they behave in nice ways with respect to sum and tensor product. Okay, so the second property is what makes them specially suited to our purpose. The character of a tensor product is in fact the product of characters. Okay, so now in addition to what I already said about a character of a highest weight module, we have this important theorem, Weyl character formula, which tells you what the character of V lambda equals. So here's, let me write down the expression. So it says it's, well, a sum over a group called the Weyl group of the Lie algebra, and there is a sign, so it's what's called the sign of W. So this term is plus or minus 1. I mean, there's an explicit way of computing it, but you can think of it as the way you have sign for elements of the permutation group, like the even and odd permutation. So it's the analogous thing in general. So you have epsilon W e to the W lambda plus rho minus rho divided by so this is the Weyl character formula. It's a sum divided by a product. The sum, as I said, ranges over, it's called the Weyl group. So the terms here are W is, it's called the Weyl group of G. The special element rho is what's called the Weyl vector, and it's half the sum of the positive roots of the Lie algebra. And I guess the thing on the bottom is clear, right? This is now just the product ranging over all the positive roots of the expression 1 minus e to the minus alpha. And notice here again that the things which appear are all, it's an element of C of H star, right? All these are formal exponentials. W of lambda plus rho minus rho is some element of H star. So you should think of this as actually happening in C of H star. But again, we sort of remark here that it's better than just being an element of C of H star once you pull the highest guy out. So let's do that here too. So I'm going to pull out this e to the lambda term and then see what the rest looks like. So let's do that. Let's pull out then e to the lambda from the numerator, okay, and call what's left as u lambda, and let's just call the denominator as d. So where u lambda is just the name I'm giving to the sum e to the w lambda plus should have been better than this. U lambda is just the alternating sum over the Weyl group. Right, so all I've done is pulled out an extra lambda from the numerator and call what's left as u lambda. Okay, and again notice that both these terms u lambda and d are both elements of that polynomial algebra. So if you, so I should probably say, observe I mean it's obvious for D, but it's also true that u lambda is an element of this polynomial algebra. Okay, so these special combinations w of lambda plus rho minus lambda plus rho, it turns out that when you, I mean it's an element of H star which when you write out will turn out to be a non-positive integer linear combination of the alphas. So this fact here that u lambda belongs here is a consequence of the fact that this particular combination, when you act a Weyl group element on lambda plus rho, the answer always looks like this. It's lambda plus rho minus some a non-positive, I mean plus a non-positive integer linear combination of the alpha i's. And so again, like we said there, we are in the same situation. You pull out the highest term and then you get an element of the polynomial algebra divided by another element of the polynomial algebra, and you can think of it as being a consequence of the Weyl character formula that this polynomial is always divisible by this polynomial in this polynomial algebra, and the result is some other polynomial, right? And that polynomial multiplied by e lambda ends up giving you the character of your representation. Okay, now yet another fact. This is these u lambdas sort of uniquely determine lambda. Okay, so knowing, in some sense, like saying knowing the numerator of the Weyl character formula determines what the highest weight is, okay, or the characters determine the representation. So in some sense it's that fact. Okay, so now let's try and prove Rajan's theorem. So I'm going to prove it in the version dash, proof of theorem dash, which means I'm assuming I have a finite dimensional simple Lie algebra. I fix n, and I take a tensor product of n irreducible representations equals or is isomorphic to a tensor product of n other. So this is what I'm given. I'm given some vi's and I'm given some wj's, and I know that both these tensor products are isomorphic, and I need to show that the v's and the w's themselves are the same up to reordering. Okay, sorry.
Crucial point is that I hope that you don't know u lambda by d is irreducible.
I'm sorry, what?
For example, u lambda by d is irreducible.
Right, then of course, yes, then you are done. Correct. It is not true. Yes, u lambda divided by d. So what Seshadri is saying is, if you take the polynomial algebra C of whatever, right, infinitely many variables, if you knew that this particular fellow is an irreducible polynomial there, then in some sense this is like unique factorization in polynomials. A polynomial can be written as a product of irreducible polynomials in only one way, right? So then you would be done. But what this is some kind of analog of that for a different family of polynomials. So you can, if you want to think of it like that, you can look at these polynomials u lambdas as being a distinguished family of polynomials here, which admit the unique, which has the unique factorization property, meaning if at all a polynomial can be written as a product of these ones, they can be written, it can be so written in a unique way. But not all polynomials will admit expressions as products of such fellows, right? So they are not as nice as the family of irreducible polynomials. Okay, so do you have a question? Okay, so tensor Vi is isomorphic to tensor of Wj's. So how would one proceed? Well, we would take characters on both sides. So you compute character of this tensor product should equal character of the other tensor product, and we know that character of a tensor product is a product of characters. So let's write the formula there. Character of each Vi we know is e to the lambda I. Maybe I should do this on the other board. So the character of the left hand side looks like this. There's a e to the lambda I, there is a u lambda I, there's a d, and it's a product over I. Same thing on the right hand side. So I should say product e to the mu j I. I haven't told you what these are. So since we know that the v's and w's are irreducible polynomials, let's give their highest weights a name. Let's call vi to be the representation with highest weight lambda I, and wj to be the representation whose highest weight is mu j. Okay, so I highest weights a name. Now when I take characters, this is what I get on both sides. Okay. Now of course the number of factors is the same, so I can cancel the denominators and pull the leading terms out. On the one hand I have e to the summation lambda I product of the u lambda i's, and on the other hand I have e to the summation mu j's product u mu j's. And again, if you think of this as being an equation in C of H star, then what it says is that these are the two leading terms. So this is one leading term and this is the other leading term. So you can think of these summation lambda I and summation mu j as being the highest weights for the tensor products. So in particular it means these two terms must actually be equal to each other, right? Or think of it like this: if you expand this left hand side out, all the terms that you will get will look like there'll be this particular term will occur, e to the summation lambda I, and all other terms will look like something smaller than this. The same on the other side, right? And so that would force you'd get inequalities both ways, that this would have to be smaller than that and that would have to be smaller than this, and so on. So this equation in fact tells you the leading terms themselves are the same, and therefore what you finally end up with is an equality between polynomials in L variables. So I said the u's are actually elements of this polynomial algebra. So now what we are saying here is a product of L special polynomials is another product of L special polynomials, and you want to say that this can only happen if the polynomials that occur on both sides are actually the same. Okay, so this is sort of the remark that Seshadri just made. If you knew, for example, that the u lambdas are all irreducible polynomials, then you would just get the theorem from here, because a product of irreducibles on one side, a product of irreducibles on the other side is a unique factorization domain, and you would conclude that these fellows and those fellows are the same. But it's not true that the u's are irreducible polynomials. So it's very far. In fact, Rajan has some recent thing on. So I think he has a criterion. So there are some obvious situations. So there are some obvious factors. So for example, if the lambda, when you write the lambda in terms of the fundamental weights, if there is a GCD between those coefficients, then you can pull out one obvious. Rajan's new theorem says that apart from the obvious factor, what's left is irreducible. So it's some statement like that. But in general, even for an, as soon as you have a GCD between the coefficients, you will get an automatic factor. So it's usually far from being irreducible. Okay, so here's an equation between polynomials. So erase these guys. So both sides are now elements of the polynomial algebra C minus alpha L, and let's give these variables names. Let me just call these x1 through xl. Okay, so here's a equation between, like I said, special kinds of polynomials. The u's are very special polynomials. Okay, so let's from here we want to conclude that these polynomials are equal, right? Up to reordering, the factors are the same. So to get a sense of what these polynomials look like, these special polynomials, let's just do the simplest case of SL2. So let's take the smallest simple Lie algebra and just figure out what these u lambdas look like. So example, let's take G to be SL2. Just 2 cross 2 traceless matrices. The Cartan's algebra is one dimensional in this case, and there is only one single simple root. So there is just one single root, simple root alpha 1. And the set of dominant integral weights in this case turns out to just be, again, integer, non-negative integer multiples of a single weight called the first fundamental weight omega 1, where omega 1 is just, well, another name for half alpha 1. Okay, so it's just a one-dimensional problem. There is just, you should think of the dual of the Cartan subalgebra as being generated by this element alpha 1, and half alpha 1 is the fundamental weight omega 1, and multiples of this omega 1 are all the dominant integral weights. Okay, so therefore, what are all the irreducible representations? So we said the irreducibles for SL2 are all given by V of lambda, where lambda is a dominant integral weight, and here of course dominant integral weights are just multiples of omega 1. So here I just have to pick a non-negative integer, and that multiple of omega 1 would give me some irreducible highest weight representation. Right? So the question now is, what do the u lambdas look like? That's all we need to really understand, right, to see if two such products can possibly be equal. So let's see what is u lambda. So let's compute this polynomial u of p omega 1. So we know the definition. It says you sum over the Weyl group. So in this case, the Weyl group, it turns out, only has two elements. So it's just the identity and the minus identity. So it's just the identity and the flip about the origin. So it's a two-element Weyl group, and so it's easy to compute u lambda from its definition. U lambda, remember, is you're supposed to sum over the Weyl group, alternating sum E w lambda plus rho minus lambda plus rho, and in this case it turns out, well, if you remember the definition of rho, it's half the sum of positive roots, and it turns out in this rho is the same as half alpha. So what you get is, you need to sort of compute with this expression. So there are two terms. If you put w equals identity, you will just get e to the 0, right? That's a 1. And if you put w equals negative identity, which has it's an odd element, so you'll get a sign there. In addition, what comes upstairs is lambda plus rho is just going to be p omega 1. So remember, lambda is p omega 1. So this is p plus 1 times omega 1. Okay, so you must reflect that about the origin. So it becomes minus of p plus 1 omega 1, from which you further subtract a p plus 1 omega 1. Okay, so it becomes minus 2p plus 2 omega 1. Okay, so this polynomial is very simple in this case, and remember again that 2 omega 1 is alpha 1, so I can rewrite this as 1 minus e to the minus p plus 1 alpha 1, and observe it is, as it should be, a polynomial in the one variable e to the minus alpha 1, right? So in general we have said that u lambdas must end up being polynomials in these L variables. Here there's only one variable, and it's a polynomial in that variable. So let's call that variable, as we already gave it a name, let's call it x1. So this is 1 minus x1 power p plus 1. In the special case of G is the polynomial we get, right? And you can see, of course, that it's it's not going to be reducible at all. It's certainly there is a 1 minus x, but also even beyond that it splits into factors, right? So this is sort of far from being irreducible. But let's see if we can prove this theorem in that case. We want to say, so what does the theorem for SL2 state? It's just a statement about such polynomials. Okay. So what we really want to prove is the following. So the SL2 version of Rajan's theorem is the following statement. It says, suppose you are given numbers P1 through Pn and Q1 through Qn, non-negative integers, such that polynomials 1 minus, let me start calling x1 as x to the pi plus 1 equals product 1 minus x to the qj plus 1. Then the p's and the q's are the same up to reordering. So there exists a permutation sigma such that pi is the same as right. So it's these are the special family, and this is the special family of polynomials that you have, and the claim is that if a polynomial can be written as a product of such terms, it can be written in a unit A, right? So if we prove this, then of course we are done. How do we prove this statement? So it should be doable just by very elementary means. So of course we know what these polynomials look like. So for example, this is sort of the cyclotomic thing, right? Well, almost. So we can easily find roots of these polynomials. The primitive pi plus 1th root of unity, or any pi plus 1th root of unity would be a root of this polynomial. So what you attempt to do is to just find roots of these polynomials, just compare roots of these polynomials. So how do we prove this statement? Well, just to make life simple, let's arrange the p's in increasing order. Let's do the same to the q's. Now we claim that the Pn and the Qn must be equal to each other. Okay? Claim the maximal fellows on both sides must be equal. Well, if not, if Pn is smaller than Qn, then what does it mean? Well, it means you look at Qn plus 1th root of unity. You take a primitive Qn plus 1th root of unity. So then consider zeta equals e to the 2 pi I divided by Qn plus 1, for example. This guy would be a root of the right hand side, but not of the left hand side, right? This is a 0 of the right hand side, but not the left hand side. Okay, so that would tell you that Pn must equal Qn. Now you can play the game the other way around. If Pn is greater than Qn, you just choose Pn plus 1 here. Okay, so unless the two maximal fellows are equal, you would certainly be able to find a root of one side that's not a root of the other. And so Pn equals Qn, which means you cancel those two terms and then you proceed by induction. Okay, so that's the proof in the case of SL2. In fact, in Rajan's proof, this is which works by induction on the rank of the Lie algebra as well as on the number of factors in the tensor product. This would be the base case. So proving it for SL2 is necessary to anchor the induction in that case. Okay, so what I'm now going to do is sort of deviate at this point from the proof. So here is an alternate proof. So observe, both sides, as I mentioned, are polynomials in the variable x, right? So we are looking at this as an identity between polynomials in x, and then using roots, trying to look for roots of the polynomials. Now let's do the following. Well, these are polynomials in x. but in particular it means they are power series in X. Okay, so let's think of just a mild change of point of view. Let's think of both these. Let's think of this as an identity between power series in X. Now both sides are power series with constant term 1. So observe that both left hand side and right hand side are, well, I'm just thinking of everything as formal power series with coefficient of x to the 0. The constant term is a 1 on both sides, right? Now what can you do to power series which have constant term 1? Well, you can invert them, but I'm going to sort of do something which is necessary, which helps in this case. Let's take log. So there is, if you have a power series whose constant term is a 1, a formal power series, there's one thing you can do to these guys, which is you can take the logarithm of such a power series. Okay, so if, and what does that mean? So I'm not doing any analysis here. So what do I mean when I say logarithm of f, where f is a power series in X? So imagine f is a power series in X whose constant term is a 1. So a power series in X, right? So potentially infinite power series. I mean it's an infinite series. So let me write it as 1 plus xi. Xi is just refers to all the rest. This whole thing is a xi. So I need to compute. So I formula for logarithm xi minus xi square over 2, xi cubed over 3, and so on. Okay. No. So so what do you mean by convergent? That's the immediate question one should ask, right? What does it mean to say that this series? In what sense am I talking about this series? Well, let's look at xi. So what's the smallest power of x which appears in xi? Xi doesn't have a constant term, right? Xi begins from x. Now when I square it, xi square will only begin from x square, and xi cubed will only begin from x cubed, and so on. So this series in the formal sense is convergent, because to compute the power of the coefficient of any power of x, it's a finite computation, right? So it's a well-defined object in the formal world. That's the reason I demand that I need a constant term here, and the rest is what I'm really manipulating over. Okay, so I can define such an object, so which is of course modeled on our usual formula for the logarithm, but it exists in the formal world, and more importantly, it has all the nice properties. For example, the logarithm of a product is the sum of the logarithms. So if I have two power series f and g whose logarithm, whose constant terms are 1, then their product also has constant term 1, and therefore its logarithm is a well-defined power series, which turns out to be the sum of the logarithms. Okay, again purely in the formal world. So this is true in a purely formal sense. Everything makes sense formally, and these two things are actually equal, as it's an identity between formal power series. Okay. Okay. So that allows us to look at this expression. Now the reason I said let's think of it as power series is, even if it were a polynomial, taking logarithm makes it a power series. Right? If you think of it as a formal logarithm, you do get a power series anyway. So let's compute log 1 minus x to the pi plus 1 summation. So the thing now looks like this. That's the identity we are looking at in C of x, and we know what both sides are. So on the one side it's the minus summation, so I need to raise this to the power, so it's xi power k over k, so this becomes x power pi plus 1 to the k divided by k, and the other side is there's a minus sign in front, x to the qj plus 1 the k divided by k. Okay, so all I have done is just use the formula for the logarithm and expanded both sides out, and notice, because of this minus, all I do is just get a leading minus sign on both sides. So I might as well make both of these plus. And now let's, if you sort of stare hard at both these expressions, we should be able to give another proof of this theorem. So let's sort of consider the left hand side. Now the first question is, what's the, so in contrast to polynomials where you always look at the degree, I mean the highest power of x, when you are in power series you always look for the lowest power of x. So here, what's the smallest power of x which appears in, say, the inside sum? So if you look at this guy, it's k equals 1, right? X power pi plus 1 divided by 1, that's the smallest power of x that would come from here. And now let's look at the entire summation. What's the smallest power of x which appears in this whole summation? And remember, I arranged my p's in increasing order. So this is x to the p1 plus 1. This guy is the leading term of this power series, right? Any other term I get is strictly bigger than this. And of course this could appear with coefficient bigger than 1, because there could be, I mean the first few fellows could be equal, right? The p's could all be equal. So I could get coefficient more than 1, but it certainly is a non-zero coefficient. So let's look at the right hand side and ask for its leading coefficient. By the same token, it's x to the q1 plus 1 divided by 1. Right? That's the leading coefficient on the right hand side, and so of course the leading coefficients must be the same. So p1 must equal q1. So right, so notice in contrast to the earlier case where we said pn and qn are equal, you cancel and proceed downwards. Here you conclude p1 equals q1, so you sort of cancel and proceed upwards. Okay, but it's the same proof. So this implies p1 plus 1 equals q1 plus 1. Okay, so you're done. So this is another proof of Rajan's theorem. But it turns out that this proof more or less generalizes without, there isn't anything too different between this and the general case. So if you have seen the proof for SL2, the proof for the general case is exactly analogous. So let's do the same thing in general. So which means I'm going to assume that G is any finite dimensional simple D algebra. I'm going to assume I'm given a bunch of irreducible representations. And again, I will assume that the highest weights are the lambdas and mu's. Okay, so let's do the same thing as before, what we did for the case of SL2. Step 1, you apply character. And the character is, we repeat the same thing we did. Each character would become e to the lambda I times the u lambda I divided by a denominator, right? So you will get e lambda I, u lambda I divided by denominator. Product of such fellows equals step 3, will cancel denominators, you cancel leading terms to just make this an equation between polynomials. So you say it's a product u lambda I equals product okay. So it's an equality between polynomials in variables, in the L variables e minus lambda 1, e minus alpha 1 through e minus alpha L. And again, as before, you think of this as actually being an identity between power series in these L variables. Okay, and observe these u's have constant term 1, just as in the case of the one variable, because the u, the 1 comes from taking w equals identity in the expression for u. Right? So the constant term in u lambda is always a 1, whether you are in SL2 or in the general case. So it's just that it's a power series in several variables. So you just apply logarithm again. So step 4. Okay, where you think of these as again being power series in L variables, and as in the case of SL2, what you need to do is to understand the leading term of these power series. Okay, so the 5th step, which is the only thing that remains to be done in the general case, as in the case of SL2, is to understand the leading term of this u lambda. So this is really the last and key step. So you want to say, okay, let's take log of u lambda, and you want to say, I should say, compute the leading term. Now I'll just no, okay. So that's the very first question you would want to ask. What do you mean by the leading term? Right. So earlier, of course, in the case of one variable, leading term meant the smallest power of x that appears. Now we use the more or less the same thing. Let's use total degree. Okay, except, so what do I mean by leading term? Well, in this case, it will mean it's the smallest degree term, total degree term, but that contains all variables x1 through xl. So you look at all the monomials which appear, but you sort of only pick the what you might call the regular monomials, the fellows which involve all variables. Okay, and amongst those guys, you pick the fellow of smallest total degree. Okay, there could be several, of course. Right now, so one needs to sort of analyze what this is. So I mean, the definition, of course, is suggested by the computations of this monomial. So here's the thing. There is actually a unique leading term. If you compute log of u lambda.
Sorry for being a little dumb. Why should they exist even one?
No, there doesn't need to. Yes, yeah, absolutely. Sure, there doesn't need to exist in some sense. It could just involve all small variables. So in a sense, I sort of jumped the gun. I think I should have sort of stated the next proposition first, which is that such a thing exists and is unique. Okay, so here's the key proposition. If lambda, so if you, just as in the case of SL2, when you write a dominant integral weight as some multiple of the first fundamental weight, I guess I'm out of time. Should I just maybe another 5 to 7 minutes? Okay, so if lambda is a linear combination of the fundamental weights, then let's look at the if you look at lambda plus rho, which is what really appears in the numerator, that would be a1 plus 1 omega 1 plus a1 a2 plus 1 omega 2 and so on. So let's call these guys, those coefficients, as b's weights. Then the statement is that there exists a unique leading monomial. So I should say there is a unique of smallest degree so in log u lambda. So if you take the power series log u lambda, it turns out that there is a unique monomial which contains all variables, which has the smallest possible degree, and this, well, what is this monomial? It's namely xl to the bl. Okay, so I mean, in a sense, it's really a matter of computation. So if you actually sit and compute with this power series, which you can do explicitly, you will find that there is a unique monomial which contains all variables, with smallest degree, and that monomial turns out to sort of carry the signature of lambda. It remembers what lambda, that monomial tells you what lambda was. If you take log u lambda, that monomial will turn out to be the fellows whose coefficients are exactly the coefficients of lambda plus rho. In a sense, therefore, if you knew this monomial, you could recover lambda back from it. Right? So it carries the signature of lambda in some sense. Okay, so that's really the key proposition, and I don't think I have time to really go into the proof of this, but given this, let's complete the proof of Rajan's theorem. So again, what is it that we needed to do? We got this far. Now we need to analyze leading terms on both sides, like in the case of SL2, right? So let's do the following. Let's take this equation and let's restrict attention to sort of the regular monomials, meaning to say you only worry about terms on both sides in which all variables appear. Okay, that's a start. So let's look at summation log u lambda I, and you only look at the regular part, by which I mean things containing all variables. Log u mu j, take just the regular part, right? And let's compare monomials of smallest degree. So let's assume so what should we do? So let's take degree of, so let's call this monomial as let's call it
Degree means you mean total degree.
total degree, yes, smallest total degree, right? So okay, so let's look at this now. So suppose you take all the regular fellows here. There's something further that I should have said here. In fact, the monomial of smallest degree containing all, there exists a unique monomial. Further, what coefficient does it occur? Okay, this monomial occurs with coefficient that we'll call C of G, which is independent of lambda. Okay, this coefficient turns out to be in fact a natural number which is independent of lambda. It is same for all the lambdas. So you take any log u lambda, you take any lambda whatsoever, compute log u lambda, and you pick that leading term. That guy always has the same coefficient. Okay, and that's what.
Could be several.
What?
There could be several leading terms.
No. There is a unique leading term, but if you change lambda and compute the leading term in log u lambda for the different lambda, the leading term coefficient is the same. Right? The coefficient is always a non-negative integer. Is a positive integer. In fact, it's non-zero. Right? It's a
The term is unique automatically equal to the
for a lambda it is unique. It is independent of, depends only on G. That's all I'm saying. Okay, so the powers of xi. So I mean the monomial itself depends on lambda, right? And there is a unique monomial of smallest total degree. The monomial is unique. There won't be two such fellows. The coefficient that comes here, that guy only depends on G. And in fact, for all the finite dimensional Lie algebras, it is 1. Okay, it's always a positive integer. Turns out to be 1 for all the finite dimensional simple Lie algebras. But I'm sort of stating it for a reason. In general, I mean, I'm eventually going to make some noises on, it doesn't really depend on finite dimensional Lie algebras. But in general, it will turn out that, for the infinite dimensional setup, it only depends on the Lie algebra, not on the highest weight that you pick. Okay.
You can write it from the Cartan matrix.
I mean, in principle, I guess if it is. Oh, you mean can you compute it that way? No, not from the Cartan matrix itself, but yeah, but we have a way of calculating. I can tell you what it is in terms. It has some nice factorization. Right, in a sense, yeah. Okay. Okay, so here's sort of the rest of the proof, right? How would you complete the proof? You look at only the terms which involve all variables, and you would say, okay, amongst the fellows on the left hand side, let's pick the the smallest degree of those. So let's order these fellows in increasing degree. So let's call that monomial corresponding to lambda as m lambda, and let's order those m lambdas in, say, increasing order. Let's assume without loss of generality that lambdas have been arranged such that the corresponding monomials have total degrees which increase. The same with the mu's. Right? Now on the left hand side, what's the let's pick the monomial of smallest total degree. That's going to be m lambda 1. Right? Because, well, there could be more than one now, because of course there are, the total degrees could be equal. M lambda 1 and m lambda 2 could have equal total degree. So, but at any rate, m lambda 1 surely appears as a monomial on the left hand side. So observe, m lambda 1 appears or occurs on the left hand side, because it cannot be cancelled by terms which come from the other log u lambdas. Right? M lambda 1 occurs in log u lambda 1, and it's the smallest guy which occurs there. Now the other log u lambdas only have terms of degree equal to this or larger than this, right? And this guy cannot be cancelled by things which come from the other log u lambdas, because, well, even if it is equal, those m lambdas are different. I mean, the lambda I is different. Okay, so this can be somewhat confusing when I'm just saying it, so you should sort of think through this. But m lambda 1 appears on the left hand side. It cannot be cancelled away by the action of by adding the remaining terms. Therefore it must appear on the right hand side also, right? It must occur on the right hand side. And so the question is, if it occurs on the right hand side, which term can it occur in, right? So so maybe to make this, so again, like we did in the proof of SL2, let's claim that these two guys must actually be the same. Right? Let's say their degrees must be equal, because if say the degree is smaller, then that term cannot appear on the right hand side, right? Things there are. So the minimum degree must be equal on both sides, definitely. And therefore if m lambda 1 occurs on the left hand side, at least for one of the m mu's, the m mu's for which the degree is minimal, at least one of them must equal lambda 1. Right? Only then can you possibly get that term. Okay, so it appears on the left hand side, therefore on the right hand side, and therefore there exists some mu j such that m mu j is equal to m lambda 1, and that sort of implies that that particular mu j equals lambda 1. Okay, so I kind of said this fast, but if you sort of work through this, you will see that this must in fact be the case. Okay, and then therefore you are done. So then you cancel and proceed, right? As before, you just cancel and proceed. So that will prove the theorem. So in some sense, it's just an analysis of the leading term. So I'll just make last couple of remarks, which is this generalizes. So I sort of mentioned in the abstract that it generalizes without any further effort to the case of the Kac-Moody algebras, because if you compute u lambda, so I mean if you look at the expression for u lambda, which is the sum over the Weyl group, alternating sum over the Weyl group lambda plus rho. If you are a finite dimensional Lie algebra, we said this guy belongs to the polynomial algebra in L variables. And in order to use our logarithm, we said, well, let's think of it as actually a power series. and then apply logarithm and so on. Now, if you were instead in a Kac-Moody algebra, which is an infinite dimensional Lie algebra, u lambda would have actually been an infinite sum or an infinite Weyl group, and your u lambda to start with would have been a formal power series. Okay, it's already a formal power series to begin with. You don't need to pretend it is 1 in order to apply logarithm. Right? So it's sort of natural in this framework that you actually are led to consider formal power series. Okay, so that's one remark I wanted to make, and then the rest of the proof follows exactly the same way. And so then of course we come to this. So when you do it, the key step is of course to find the leading term, which I said is given by this proposition, which says that the leading term is independent of lambda, only depends on the Lie algebra you start with. Okay, and it's always a positive integer. It turns out that this guy has sort of coming to this question of can it be computed and so on. It sort of has this nice interpretation. This is actually the dimension of a certain root space, which is always 1 if you are in a finite dimensional Lie algebra. All root spaces are 1 dimensional, but it's also in fact the same as the number of conjugacy classes of Coxeter elements of your Lie algebra, of the Weyl group, which is also 1 in the case of finite dimensional simple Lie algebra. Okay, a Coxeter element is just a product of all the simple reflections. So any product of simple reflections is called a Coxeter element. Okay, so it's true that so it's a fact that for a finite dimensional Lie algebra, all Coxeter elements are conjugate to each other. If you are in a and so it's the number of conjugacy classes, it turns out. So therefore, I mean it's 1 for all finite dimensional Lie algebras. But it also makes it clear that it's always a positive integer. It counts the number of conjugacy classes of Coxeter elements. So that tells you that it's always a positive integer, for example, in the other cases. And there are sort of ways of, it also has a purely combinatorial characterization in terms of these things called chromatic polynomials or Tutte polynomials or the graph and so on. So you can actually compute these guys using certain recurrence relations. So yeah, so there are ways of computing it in terms of the graph. Okay, I'll stop.